So part of becoming a mature user of mathematics is to develop a desire to understand where things come from, especially formulas that we're asked to use. So in this section, we are given the product and quotient rules for finding derivatives, and if we're going to focus in this video on the product rule and identifying where it comes from or justifying it. So the derivative of a product of two functions, what we're told is that it is going to be equal to the derivative of the first function times the second function plus the first function times the derivative of the second function. And it's kind of a counterintuitive rule. So you really should ask the question, why does the product rule look the way that it does? Why isn't it just, if we want to do d dx of f of x times g of x, why don't we just take the derivative, the product of the derivatives, for example? Why can't we just do that? We can't. They're not equal. But so what we want to do is justify the product rule. So let's start off with a function p of x, and let's say p of x is the product of two other functions. So we're taking a product of two functions and giving it a function name. So if you were going to take the derivative of p of x, you would use the definition of a derivative. The definition of the derivative is, hey, get the slope of the secant line and then take the limit as h goes to 0 of the slope of the secant line, and this will give you the slope of the tangent line, which is the definition of the derivative. And a lot of you in the homework have been using in the denominator down here a delta x. And what we want to make sure is what we want to make sure that we understand is that h is just a name for delta x. So we don't need to write delta x over and over and over again. We just say, hey, let h be delta x. H is much simpler to write, and we're going to take the limit as h goes to 0. And what we want to recognize is with the difference quotient, this says plug x plus h. This right here is saying plug x plus h into p of x. But if we do that, that's the same as plugging x plus h into f of x and g of x. So we'll do that on the next line. We'll say, hey, p of x is just the function f times g. Let's go ahead and plug x plus h into f of x times g of x. So here we've done that. And p of x is really just f of x times g of x. So replace p of x with f of x times g of x. So we're applying the difference quotient, taking the limit as h goes to 0 for this guy right here. And then what we want to recognize is that the form of the derivative, if we could get the limit as h goes to 0 of f of x plus h minus f of x over h, this would just equal the derivative of x. And if we could get the limit as h goes to 0 of g of x plus h minus g of x all over h, this is just the definition of the derivative of g of x. So part of the next step is just a clever manipulation to try to get these two forms to pull out of this ratio. So it looks complicated at first, but if we talk it through, it's not too bad. Right here, we're subtracting. This is the same. This first part right here is exactly the same as the previous line. And the minus f of x g of x is exactly the same as the previous line. So the only thing that's changed is this bit right here in the middle. And if you look carefully at it, what you'll see is that that adds up to 0. So in effect, nothing has changed, right? Negative f of x times g of x plus h plus f of x times g of x plus h is just 0. And the reason for doing this is we're trying to get this f of x plus h minus f of x all over h form. So we've introduced an f of x here that can be subtracted from the f of x plus h. And we've multiplied it with the g of x plus h, which was already on this first term, so that we can factor out a g of x plus h, which will give us this difference up here that starts to look like a derivative. And then the issue is subtracting this will give us what we want, but you can't just arbitrarily subtract something from the numerator of a ratio and have the ratio stay the same as it was. So we add the same amount on so that the net result is an addition of 0. And when we add the same amount on, what we see is that the f of x shows up in two spots and can be factored off of g of x plus h minus g of x, and we start to get a numerator that looks like the derivative of g of x. So the next step is just to do the factorizations. So on the first two terms you factor off a g of x, and then on the second two terms you factor off the f of x, and then what we want to recognize is that we can break this previous statement into two separate fractions if we put both of them over h. And so that's what's happened here. We've taken this addition, we've separated into two separate fractions, each of which has to be over h. And for each of those two fractions, we factor off the common factor. So g of x plus h gets factored off of the first set, and the f of x plus h gets factored off of the second set. So it's just an algebraic manipulation of the previous line, but this right here starts to look like the derivative of f, and this right here starts to look like the derivative of g. So now it's all about homework 2. Homework 2 was about analytic or algebraic calculation of limits. And so one of the things that we identified when working through homework 2 is that if we have the limit of a sum of two things, that can be broken into the sum of the limits, that we can take the limit notation and distribute it into each of the two pieces, and it's an equivalent statement. So this is part of why homework 2, which was the algebraic calculation of limits, was so important, because it gives us the tools that we need to develop the formulae for derivatives. So now I have the sum of the limits, and then another result from homework 2 was that if we have the limit of a product of two functions, that we can break that up into the product of the limits of the two functions. So the next step is just to make that manipulation. Instead of applying the limit to the product, we take the product, there's the multiplication coming down, you take the product of the limit applied to each of the two terms. And we do the same thing here. The limit of a product becomes the product of the limits. And once we have it here, we're essentially done. We want to recognize that the limit as h goes to 0 of the difference quotient, that's just the definition of derivatives. So this limit right here is f prime of x. And here I have the limit as h goes to 0 of the difference quotient being applied to the function g, which is just the derivative of g. So the only thing left to do is to clean it up in a final step and recognize that this guy right here is the derivative of f. And if we take the limit as h goes to 0 of g of x plus h, that's just a matter of plugging 0 in for h. We get x plus 0 is x. We get g of x. And then plus the limit as h goes to 0 of f of x is just f of x, because there's nowhere in that function to even put an f. And this limit right here is g prime. And then this is the product rule for finding derivatives. So that's where it comes from. It comes from taking the definition of derivative, applying it carefully to the product of two functions, and then using the algebraic manipulation of limits from homework 2 to get it down into a form that is useful.